Hi everyone. Today we're going to study direct trigonometric functions or ratios. We have here a right triangle. First, let us label the parts of the right triangle. We can see here the small square that denotes right angle, and the side opposite is what we call the hypotenuse. Then, for the two angles here, let us name one angle to be theta, and the side here is the opposite side of theta. And the last side will be called the adjacent side of the angle theta. We will now specify direct trigonometric functions. We will begin with the sine theta. The symbol for sine is sin theta, and this is equal to the ratio of the opposite side over the hypotenuse. The next function is cosine theta. The symbol is cos, and this is the ratio of adjacent over the hypotenuse. The next function is tangent theta, and the symbol is tan. This is the ratio of the opposite side over the adjacent side. There is a popular mnemonic to help us remember quickly the three functions here. This is the SO, KA, TOA. The SOH is for the sine. The S here is the first letter of the sine. The O is for the opposite, and the H is the hypotenuse. The Ka is for the cosine, with that first letter C to denote cosine. The A is adjacent, and H is the hypotenuse. TOA is for tangent, where T is the first letter of the tangent. The O is the opposite, and A is for the adjacent side. So, TOA. We'll go now to reciprocal functions. Let's begin with secant theta, with a symbol SEC, and this is the ratio of hypotenuse over the adjacent side. This is called reciprocal function because this is the reciprocal of cosine. The next function is cosecant theta, with a symbol CSC, and the ratio is hypotenuse over opposite side. This is the reciprocal of the sine. The next function is the cotangent theta, symbolized by COT, and this is equal to the ratio of adjacent over opposite side. This is the reciprocal of the tangent. Let us have example 1. Using the triangle shown below, evaluate sine alpha, cosine alpha, tangent alpha, secant alpha, cosecant alpha, and cotangent alpha. In this triangle, the angle alpha is here. So the opposite side is here with the length 4. This is our right angle, and opposite to that is the hypotenuse with length 5. And the side here is the adjacent side with length 3. Let us now start evaluating the ratios. Let's begin with the sine alpha. The ratio is opposite over hypotenuse. The opposite is 4 and the hypotenuse is 5. So this is 4 over 5. Next is cosine alpha. The ratio is adjacent over hypotenuse. The adjacent side is 3 over the hypotenuse, which is 5. So cosine alpha is 3 over 5. Next is tangent alpha, and the ratio is opposite over adjacent. The opposite is 4 over the adjacent, which is 3. So tangent alpha is 4 over 3. Next is secant alpha. The ratio is hypotenuse over adjacent. Hypotenuse is 5 over the adjacent, and that is 3. So secant alpha is 5 over 3. Next is cosecant alpha. The ratio is hypotenuse over opposite. Hypotenuse is 5 over the opposite, which is 4. So cosecant alpha is 5 over 4. Last is cotangent alpha. The ratio is adjacent over opposite. Adjacent is 3 over the opposite, which is 4. So the cotangent alpha is 3 over 4. So we are now complete with our ratios. Let us have example 2. Given the triangle shown in the figure, find the values of all trigonometric ratios or functions of the angle alpha. The angle alpha is here. We have the length of two sides, 15 and 8. The length of one side is missing. That side is the opposite of the right angle, and that is the hypotenuse. So first, we will calculate for the hypotenuse. We will use the Pythagorean theorem. We will assign letter C to the side which is the hypotenuse, and the formula will be C square equals A square plus B square. Substituting now the values, we have the C square equals 15 square plus the 8 square. Simplifying further, the 15 square is 225 plus 8 square is 64. Then we will add the two numbers, it becomes 289. So C square equals 289. We will get the square root of both sides. Only C will come down here, and we will take the square root of 289, which is equal to 17. So the value C is 17. Then we will start writing our trigonometric ratios. Let's begin with the sine alpha. We know the ratio is opposite over hypotenuse, and that is equal to 8 over 17. The next is the cosine alpha. The ratio is adjacent over hypotenuse. The adjacent is 15 over the hypotenuse 17. So cosine alpha is 15 over 17. The next is the tangent alpha. The ratio is opposite over adjacent. The opposite side is 8 over the adjacent, which is 15. So tangent alpha equals 8 over 15. The next is secant alpha, and the ratio hypotenuse over adjacent. The hypotenuse is 17 and the adjacent is 15. So secant alpha equals 17 over 15. Next is cosecant alpha, and the ratio is hypotenuse over opposite. The hypotenuse is 17 over opposite, which is 8. So cosecant alpha is 17 over 8. Last is cotangent alpha, and the ratio is adjacent over opposite. The adjacent side is 15 over opposite, which is 8. So cotangent alpha is 15 over 8. We have now written all the trigonometric ratios, and this is now the final answer. Example 3. Given tangent A equals 4 over 3. Find the other trigonometric ratios of the angle A. We know that tangent A equals opposite over adjacent. In the problem, given is this is equal to 4 over 3. That means opposite or O equals 4 and A equals 3. We have this triangle. This is the angle A. Angle B is a right angle. We have this side 4 and this side here as 3. We need the hypotenuse, which is the H. That is the side AC. By Pythagoras theorem, we write H square equals O square plus A square. We substitute the values 4 square plus 3 square. The right side becomes 16 plus 9, and that is 25. We will take the square root of both sides. So H equals square root of 25, which is simplified into 5. Now let us write the other trigonometric ratios. We begin with cotangent A. That is the reciprocal of tangent. The tangent is 4 over 3. That means cotangent is 3 over 4. Next is the sine of A. That is opposite over hypotenuse. Opposite is 4 over hypotenuse. That is 5. So 4 over 5. Then cosine A, adjacent over hypotenuse. Adjacent is 3, while hypotenuse is 5. So we have 3 over 5. Next is the secant A. This is the reciprocal of cosine. So cosine is 3 over 5. Secant is 5 over 3. And the last is the cosecant A. This is the reciprocal of sine A. Sine A is 4 over 5. So cosecant is 5 over 4. Example 4. Consider triangle ACB, right-angled at C, in which side AB equals 29 units, side BC equals 21 units, and angle ABC equals theta. Determine the value of cosine square theta plus sine square theta. We have the figure here, and we need to find this side, which we write as small b. By Pythagoras theorem, we write 29 square equals 21 square plus b square. We simplify the squares. We have 841 equals 441 plus b square. We transpose the 441 on the left side. It becomes negative. Or we can rewrite this as b square equals 841 minus 441. The difference is 400. When we take the square root of both sides, the square root of b square is b equals the square root of 400, which is simplified as 20. Now let us take the sine theta equals opposite over hypotenuse. Opposite is 20 over 29, and that is the hypotenuse. This is the value of sine theta. For cosine theta, adjacent over hypotenuse. Adjacent side is 21 over hypotenuse, which is 29. Now let us evaluate cosine squared theta plus sine squared theta. When we substitute the values, we have 21 over 29, that is squared, plus 20 over 29, which is squared. When we simplify the squares, we have 441 over 841 plus 400 over 841. When we add these like fractions, we have 841 over 841, which is equal to 1. This is the final answer. Example 5. In a right triangle ABC, right angled at B, if tangent A equals 1, then verify that 2 sine A cosine A equals 1. We have the figure here. We know that tangent A equals opposite over adjacent. In our figure, the angle A is here, and tangent A equals the side BC over side AB, which is equal to 1 based on the problem. That means BC equals AB. We can assign a value here, let's say value K. Now, by Pythagoras theorem, we write the hypotenuse, which is the side AC, which is squared, equals K squared plus K squared. The right side is simplified into 2K squared. Then we will take the square root of both sides. The left side becomes the side AC, that is the hypotenuse, equals the square root of 2K squared, where we can simplify as K square root of 2. Now let us take the sine A, which is opposite over hypotenuse. Opposite is K over hypotenuse, that is K square root of 2. We can cancel the K, and that is now sine A equals 1 over square root of 2. Now cosine A, that is adjacent over hypotenuse. In the figure, that is adjacent equals K over hypotenuse, which is K square root of 2. We can simplify by cancelling the K. So cosine A is 1 over square root of 2. Now let us verify. 2 sine A cosine A equals 1. When we substitute the values, we have now 2 times 1 over square root of 2 times 1 over square root of 2. When we simplify the left side, it becomes 1 equals the right side, which is also 1. Example 6. In triangle OPQ, right angled at P, the side OP equals 7 cm and OQ minus PQ equals 1 cm. Determine the values of sine Q and cosine Q. This is our figure. The side OQ is the hypotenuse. In the given it says OQ minus PQ equals 1 cm. We can find the value of OQ with respect to PQ. We transpose this negative PQ to the right. So OQ equals 1 plus PQ. By Pythagoras theorem, we have the square of OQ equals square of PQ plus square of OP. We can substitute the values for OQ as 1 plus PQ. That is squared equals the square of PQ plus the OP is given as 7 cm. So we write here 7 square. We expand the left side. It becomes 1 plus 2 PQ plus the square of PQ equals the right side now square of PQ plus 49. Both sides here have the square of PQ that we can cancel. So we simplify this as 1 plus 2 PQ equals 49. We transpose this constant 1 to the right. It becomes negative 1. So 49 minus 1 is 48. Then from here, we divide by 2. We will get the value of the side PQ, and that is 24. Now for the OQ, that is the hypotenuse, that is 1 plus PQ. We substitute the value of PQ as 24. We will get the value of OQ. So that is OQ equals 1 plus 24, which is 25. And we can write it here also. Now let us get the sine Q, which is equal to opposite over hypotenuse. In our figure, the Q is here. So opposite is 7 over hypotenuse, which is 25. This is the value of sine Q. For the cosine Q, we have adjacent over hypotenuse. Adjacent is 24 over hypotenuse, which is 25. This is now the value of cosine Q.